with the full stress state at point A. So the first thing we need is we need to know what are the internal loads at that section. So we start by cutting through the plane. Then once we're at that plane, we go inside the cross section and see at what point we need to know the stress. Because the loads occur on a cut plane, stress always occurs at a point in that plane. Because the stress can vary from one side of the opening to the other in some cases. When we saw like P over A, we assumed that that was constant throughout the entire cross section. But we got to bending stress, transverse shear stress, all of those varied along the cross section. So the point of interest is very important. Right, so we start with our figure. We want to know at section AA, what are the 6 internal loads we have that we're going to have to consider what stresses they cause at point A. In this case, we were not given a coordinate system. We have to establish one. Right, so I'm going to locate my coordinate system for convenience at the top of my object here. I'm making an internal cut at 5 feet down. That's where my section is. That's where the AA section is. So I don't need to solve for the reactions at the bottom where it's built into the ground, because in this picture, I'm cutting it off before I have to see what those reactions are. So I'll start with what are my applied forces. Well, I have 2 of them applied at the end point here. I have that 300-pound load in the what I just called the Y direction. And a 400-pound force along what I'm calling the X direction. All right, so those are my applied forces. What is happening at the cut surface? Let's first look at that internal normal force, because that's going to determine the direction of our torsion. So the internal normal force always comes out from the cut surface of our object. So we're going to have an internal normal force P, and the direction of it, again, is always normal to the surface of the cut. And it comes out from the surface of the cut, which then we can interpret a positive value for P, meaning tension, a negative value, meaning compression. Okay, so P is in, according to my coordinate system, in the negative Z direction, but it's pointing that way because that's the outward normal from my cut surface. Then the torsion is determined, or our assumption of direction of torsion is determined by it goes positive around that P direction. So we'll have that internal torsion T that's positive using right-hand rule around P. Right, so again, the direction of P, the direction of T are determined by the outward normal from our object, or from the cut surface. We're in 3D, so we're going to have 2 components of shear force. So really it is only a shear force acting in one direction, but we split it into components because mathematically it's easier to solve that way. So I can split it into 2 components that are parallel to that cut surface. So for simplicity, I can just use the coordinate system I established here. So one component of my shear force I can call Vy along the positive Y direction. And the other component I can call Vx along the positive X direction. The direction of these are arbitrary, but it's easier if I just follow the coordinate system I've already established. But they have to be parallel to the surface of the cut. The surface of the cut is in the XY plane. So that's why I can split it into an X component and a Y component. And along with the 2 shear forces, there's also going to be 2 components of an internal bending moment, M. And those I can also assume are positive around those same directions. So I'll have an mx and an my. So again, two components of internal bending moment, two components of my internal shear force. I have my normal force, I have my torsion. So the first step in solving these is we need to find what are the internal loads at that cut surface. Right, so if we start in the x direction, so I chose x to be along this direction. The forces I have are the 400 pounds, that external load, and I have v sub x. So that internal shear force Vx, negative 400 pounds. So I will make a second drawing of all these forces acting on the plane of my surface. And in that case, I want everything pointing in the right direction. So according to this, it should be pointing in the negative x direction because I got a negative 400. In my y direction, I have my applied force of 300 pounds. I have my v sub y. So at this surface, Vy is negative 300 pounds. And in the z direction, I have my internal normal force P pointing in the negative z. And that is the only force acting in the z direction, so my internal normal force will be 0. Right, then I want to find my sum of moments as a vector. It's going to be easiest if I choose what I'm going to call point Q here to take my moment about. So what is the moment around point Q going to be? What is going to contribute to that moment?
Each moment is going to contribute for its own axis, like mx, I, and then my, j.
Right, so mx acts around the I direction. I assumed it was positive. My acts around the j direction. I assumed it was positive around the j or the y direction. The torque, or the internal torsion T, is acting around the negative z direction. So it will be a negative T k hat. Again, the direction of T was determined by the direction of P, the outward normal from the cut surface. So according to my coordinate system, though, it's a negative T. And then what else causes a moment around point Q?
300 pounds.
Not only the 300 pounds, but the 400 pounds also. So I have a force that's a distance away. So remember, I have to use the cross product here. It's R cross F. So I have to go from Q to where my force is being applied. I have to go 5 in the positive z direction. And then I have to go 1.5 feet in the positive y direction. And my forces at this point are 400 in the x, 300 in the y, and 0 in the k. I expand that cross product as we did before. I group all my I terms, j terms, and k terms. So if I group all my I terms together, I get an mx minus 1500, have I hat components, my plus 2000 are my j hat terms, and negative 600 minus t are my k hat terms. I now can split this one vector equation. I can equate each of my components or each of my coefficients equal to 0 individually. So I'll get that mx is 1,500 foot-pounds My is going to be a negative 2,000 foot-pound. And my internal torsion T, negative 600 foot-pounds. Now what we want to do, we have the signs and the values. We want to draw another picture so that we can see what does our actual cross-section look like. Because in this picture, we didn't care if was it round or was it square. The loads don't care what the shape of this is. The stresses do. So I'm going to draw a second picture that actually is going to look at the cut surface. And in this problem, we were looking at what is the stress state at A specifically. So what I'm going to do is I'm going to take this and I'm going to view it from the bottom where that cut is being taken so I can see where the force is acting and what point am I looking at. So I'm going to take this and I'm going to orient it as though I'm looking at it from the bottom of this pipe. So I want to draw what this coordinate system is. So I'm sitting on the z-axis, looking in the positive z direction here. So z is going away from me in the positive direction. So this is just a reorientation of this viewpoint. And now, from this cross-section, first of all, looking here, I can see where A is. A is going to be, from this viewpoint, the bottom of my cross-section. So I want to copy onto this picture the forces, the moments that I already found, but now facing the correct direction. So for example, Vx, I assumed was along the positive x-axis. It was negative, so it's actually along the negative x-axis. So I'm going to have a shear force, oops, just broke my own rule. A shear force along the negative x-axis with a value of 400 pounds. So really it's acting in the center, but so it's not too cluttered. This is just a shear force acting down on the face of this. Vy, I assumed was along the positive y-axis. It too was negative. So on this picture, I can draw it in the correct direction. I'm going to have a shear force of 300 pounds acting in the negative y direction. And this is important because the directionality of these is going to affect the shear stress on the element at A. Because the direction of V is also going to determine the direction of my shear stress. We found P was 0, so I won't even draw it in this picture. T we found to be negative 600 foot-pounds. My assumption was that T was positive around the negative z-axis. This means it's positive around the positive z-axis. So my z-axis goes into the board, so my torsion T is going to be positive around that z-axis into the board, 600 foot-pounds. MX, assumed it was positive around x, and it is. So I'll have a 1,500 foot-pound moment around the positive x-axis. So that will be in this direction. Right, so again, T is around the z-axis. This 1,500 is going to be around the x-axis. And my My, I assumed was around the positive y-axis. It's actually around the positive, it's around the negative y-axis. So around the y-axis, around the negative direction, I'll have this 2,000 foot-pound moment. So I potentially will have 5 loads that will then cause 5 stresses on my element at A. However, some of these are going to drop out. So in our list of things to consider, if we go in order, say, we will first consider what's the normal stress due to the internal normal force from P. In this case, P is 0, so there's no normal stress due to the internal normal force. So we don't have to worry about that. Right, so that is out of the way. So we can move on to the next thing that causes stress, at least if we go in the same order as we just looked at. Let's look at shear stress caused by internal shear forces. In this case, we have two internal shear forces, the 300 pounds and the 400 pounds, and both of them can potentially cause a shear stress at point A. However, here, right, so A is at the bottom. This is like the other shear stress ones, transverse shear stress ones we looked at. We know shear stress is maximum along the neutral axis and 0 at the top and bottom. So with respect to the 400-pound shear force that's acting along the x direction, it would have 0 effect at the bottom and 0 effect at the top. However, from the viewpoint of the 300-pound load, where is A located with respect to the 300-pound load? Right, it's perpendicular, and it's along what axis specifically? Which is also, right. So with respect to that 300-pound shear force, A is along that neutral axis. So we now have to think not only along the vertical, but along the horizontal. We have two neutral axes to worry about because we can have loading along now two directions. So again, with respect to the 400-pound load, it's at the bottom of that. It's furthest from the neutral axis. But from the respect to the 300-pound load, it's actually on the neutral axis that's perpendicular to the 300-pound internal shear force. So the 400-pound load will not cause a shear stress at A, but we will have a shear stress caused by the 300-pound shear force, and we have to calculate what that shear stress is. Right, so remember, we have to use VQ over IB. While we're here, we're going to need to use I for another calculation. So I'll just calculate that right here. For a hollow ring, the moment of inertia will be pi over 4 times the outside radius to the fourth minus the inside radius to the fourth. As a reminder, they told us the outside radius was 2.5 inches. And the inside radius is 2 inches. So 18.1 we'll call it. All right, because we're going to need to use that in this calculation and in the moment calculation. All right, so some of this we already have. So the V we are told is 300 pounds. At this point, the sign on V does not matter, but when we draw the stress cube associated with this, it will. So we'll see kind of in our interpretation what this is going to mean. V is 300 pounds. I, we just calculated 18.1 inches to the fourth power. And now what we need to do is look at what is Q and what is B for this shape. So A is located at the neutral axis here. So to get our Q and our B, we can make our mini shape everything above or below the neutral axis. In this case, it's symmetric, so it doesn't matter. So I'll just take everything in this case to the left of the neutral axis to be my mini shape. Right, so the radius, the outside radius is 2.5, the inner is 2, meaning that this length is 0.5 inches. But remember, I'm cutting through 0.5 here and 0.5 here. So in total, I've cut through 1 inch of material for this mini shape. Right? Again, the thickness is 0.5, but there's 2 parts of it that I cut through. Right, so if I'm interested in finding Q, Q is just A times Y tilde. So all I want to know is what's the total Q for this shape. So I can break it down into a solid hemisphere and then a cutout hemisphere, shape number 2 here. So for shape number 1, its area is going to be pi times 2.5 squared over 2, since it's a half circle. So its area is going to be 9.82 inches squared. Then the inner shape that I have to subtract out will have a negative area. In this case, it will be pi times 2 squared over 2. Or negative 6.28 square inches. Right, so again, pi r squared over 2, but we're using the inside radius in this case. And it's cut out, so it's negative. Y tilde is the distance between the neutral axis and the centroid of each of these pieces here. Right, so piece number 1 is going to have its centroid located at 4r over 3 pi from the base of the circle. Now in this case, the base of the circle is also the neutral axis. So if you're using the table method here, it's only Q if this is being measured from the neutral axis, not being measured from the base of the shape itself. So keep that in mind. This is, in this table, distance from the centroid of our shape to the neutral axis. So because they share this, I can just plug that right in. So for the outer shape, when I use 4r over 3 pi, 4 times 2.5 over 3 pi will be 1.06. And for shape number 2, it will be 0.85. So 4 times 2 over 3 pi. And then the Q is just the product of these two values here. I get 10.4. I get negative 5.34. My Q value, I get a 5.06. Okay. I have the V. I calculated the I before. This is the Q when I cut it at the neutral axis. And I cut through a total of 1 inch of material. So I can find that my shear stress due to the 300-pound internal shear force is going to be, if I can find it here, 83.8 psi. What I want to do is now draw what's the effect on the stress cube, this little differential element at A, due to this stress. Because at the end, I have to add them all together. All right, so this stress cube is going to be oriented the same way as this XYZ coordinate system. So what I do is I want to see at what face or on what face or faces does this stress act and in what direction. This is a shear stress, so it's going to act parallel to a face, and it's going to act in the same direction as the shear force that caused it. I have 300 pounds going to the negative y direction, so on this face of A, I'm going to have my shear stress pointing in that same direction. Now, with shear stresses, everything has to be in static equilibrium here. So if I have a force or amount of stress going to the left, I'm going to also have, it's tough to see in this picture, but on the back face of this, I have to have an equal and opposite force to counteract the stress going to the left. Because not only does the whole thing have to be in equilibrium, every stress cube that we can make out of it also has to be in equilibrium. Right, so this stress goes to the left. To balance it out, there must be a stress on the back going to the right. But what happens to my stress cube if I have, you can think of it because it's so small, think of it as a force here. If I have force on the front face going to the left, a force on the back face going to the right, what is going to happen to my cube? Right, it's going to be spinning, which means it's not in equilibrium. So to balance out that spinning, I also get a shear stress on the side face that's going to counteract that spinning. So the stress cube from this stress is going to look like this. On that front face that we can see, it's going to be being sheared to the left. The back face is going to be sheared to the right. And then those sides are going to be sheared in the opposite rotational direction. So when we look at this, what we're going to see is these arrows always meet at the corners. That way, the rotation is balanced out. And it has a value, all of them, of 83.8 psi. All right, so the 400 is taken care of. It had no shear stress where A is. The 300 pounds is taken care of. We now want to consider the other three loads here and what stresses they are going to put onto our stress cube at A. So I'll get rid of this in the interest of room. Let's look at the bending moments next. We have a bending moment of 2,000 foot-pounds. We have a bending moment of 1,500 foot-pounds. Which one of these will not create a stress around A? Or at point A? Which one will not introduce a normal stress? In the respect of this moment around the x-axis, A lies on that neutral axis. So it lies on the axis perpendicular to, or the axis that this rotates about. So remember when we talked about bending moments and bending stress, it's max at the top and bottom, and 0 along the neutral axis. From the viewpoint of the 1500, A is on that neutral axis. So that will not create a bending stress. However, the 2,000 foot-pounds, which is bending around the y-axis, or really the negative y-axis, will create a bending stress at point A. So the 2,000 foot-pounds, we have to find what is the normal stress due to that loading. So again, we can use negative my. Here I'm actually going to edit it a little bit. When we're talking about beams where we have a nice definition of a positive moment, a negative moment, the negative my over I is great to use because m has an appropriate sign, y has an appropriate sign, and we always know if it's tension or compression. For these problems, I recommend always just using my over I, but be cognizant of should it be in tension or should it be in compression. So from the picture here, if I'm bending around this negative y-axis, should this be a tensile or a compressive stress at point A?
Tension.
Right, it should be tension. Because of this moment, I'm going to be pushing in at the top and pulling out from the bottom. So from here, I'm going to just manually say it's my over I, but I know that because of the direction of this moment, it's going to be pulling out everything below the neutral axis, putting it into tension, and pushing in everything above the neutral axis, putting it into compression. So I know, I'll put a note out here, this is going to be tensile. Right, we already calculated I, so that part is done. It's 18.1 inches to the 4th power. Again, I'm going to ignore, for these combined loading problems, any sign I would have on M and Y, and take out that negative. I already know it's in tension. So the Y value is just going to be the distance from the point I want to know the stress of to the appropriate neutral axis. In this case, what is the distance between A and the neutral axis with respect to the 2,000 foot-pound load? Right. So point A is the outside radius away from that neutral axis. Again, with respect to the 2,000 foot-pounds, the horizontal neutral axis is what I'm considering. And finally, what will the moment be? What is the value of m that I want to use here? This is in inches, this is in inches, so I need to give her 2,000 foot-pounds to foot inches. So what do I need to multiply 2,000 by?
12.
Right, 12, not 1 over 12, but just 12. Now this is in foot inches, and now my units are, it's in pound inches, not foot inches. Pound inches, inches, inches. So my result here will be in PSI. So from the bending moment, keeping it in PSI, I get 3,310 PSI. Again, I know it's tensile. I manually said it was tensile from looking at my picture. So I want to see how does this stress now go onto my little stress element at A. So how is this stress pushing or pulling on A? It's a normal stress, so it's going to be normal to the surface of this cube. It's tensile, so how, if we look at this front face here, this moment is going to be pulling out on the front of this cube at A. So this normal stress is going to be pulling out this way at 3310 psi. And because it has to be in equilibrium, I'm also going to be pulling out on the back face with an equal and opposite value, 3310 psi. All right, so the 2,000 foot-pounds is done, the 1,500 foot-pounds is done. The last thing we have is to look at the torsion of 600 foot-pounds. Right, torsion causes a shear stress, and we know the formula is T rho over J. So another quantity we need to calculate is the polar moment of inertia for this shape. Remember, for a hollow ring, or for a hollow ring, it's going to be pi over 2 outside radius to the 4th minus inside radius to the 4th. So our J for this, 36.2 inches to the 4th power. A in the picture is on the outer diameter, so rho is 2.5. Remember, in the T rho over J, rho is your distance from the center of the cross section. So A is 2.5 from the center. And T is going to be our torque, or our internal torsion. Again, it's in foot-pounds. We have to convert it to inch-pounds. So 600 times 12 is going to be our torque in inch-pounds. The stress then caused by this torque is going to be 497 psi. So I have to apply this again to my stress cube that's located at A. It's a shear stress, so it's parallel to that front surface. But in what direction should it be pointing is what we have to look at. Across the front and to the left. So why is that? If we look at the way the torque works, which is different than the others, well, the bending stress also changes. But depending on where this is located, that direction of stress is going to change. Because at the top, that twisting that's twisting it this way and shearing it this way is actually going to be in this direction. If it was an element down here, now the torque is pulling that piece of it down. It's pulling this piece of it to the left, this piece up. So it's always going to be in a direction tangent to the circle, I guess is the best way to think of it. So when we're at the bottom end, it's going to be based on is this T clockwise or counterclockwise. So at the bottom, this piece, due to that torsion, is going to be shifted tangent to the circle, so a little bit to the left is that shift. So that's the direction at A due to that torque. So on the front face, it's being pulled to the left. And like we saw in the last one, where we had shear stress, we have to balance that out to make the full stress state. So at point A, it is pointing in the same direction. The shear stress points in the same direction as it did due to the shear force. That's not always the case, though. And this has a value of 497 psi. There was no internal pressure. We didn't have to worry about that. So we've accounted for all of the things that cause stress at point A. It turned out there were 3 things that caused stress at point A. The last step then is we have to see what's the total state of stress. This is where we now combine everything we have to see what all at once happens at point A. So since we already drew the stress cubes, it'll be fairly straightforward to do. I just add up all of the normal stresses. In this case, there's only one, so I'll just copy that exactly. And then I have to add up all of the shear stresses. In this case, I have one shear stress where on the front face it points to the left. I have another one where it also points to the left. So what will the total shear stress be in aggregate for this object? So again, this pulls the front face to the left, this one also to the left. So in total, what happens according to the shear stress? Right, they're going to add together because they both go in that same direction, so it's an additive effect. And right, we just have to add the 83.8 to the 497, and then it's going to be, I'm trying to draw on the back face here. The shear stress state then in total is going to be 581 psi.